All right, so we left off talking about what about quantitative data. That first portion was specifically focused on proportion, so you should think categorical data. But what about quantitative data? Can we do the exact same type of analysis of looking at the sample distributions for quantitative? And we can. And even better, not only can we use all of the same concepts, but it's almost the same model. So let's get into this a little bit. Like other statistics computed from a random sample, a sample mean also has a sampling distribution. So if we collect a sample, find the mean. Take another sample, find the mean. Take another sample, find the mean. And then we put all of those means on its own distribution, we will again see this normal distribution. So a simulation will give us a sense as to what the sampling distribution of the sample mean might look like. So if we were all in person, I would say, let's start with a simulation of many tosses of a die. So using a die on your calculator, roll a die 20 times. Now, to keep you guys just a little bit active, why don't we pull up our friendly neighborhood TI Inspire and look at what we have here. So I just pulled up a list in a spreadsheet, and I said roll. And I said a random integer from 1 to 6, and I want to do it, let's say, 20 times. That's what we asked you to do. It's going to overwrite those, and we got 5, 6, 1, 3, 6, 4, 4, 1, 1, 1, 6, 3, 6. Well, why don't we look at it as a histogram? And if we were in class, we would put all of these data points on the board, and we would say, what would you expect to see from our rolls? So let's just simulate our class. Instead of me doing it 20 times, how about I roll it 200 times? And as we roll the die more and more, again, a histogram is a good visual of what these numbers will look like. What should we expect to see? And note, this is a simulation, so we should be getting about an equal number of 1s and 2s and 3s and 4s and 5s and 6s, but we have a little bit of variation, which is to be expected. So to go back to our notes, a histogram of the results from our class might look like this. And so how do we do? We should get 1, 6, 1, 6, 1, 6, 1, 6, 1, 6 of all of these different rolls, but because experimental data is going to be different than theoretical data, there's a little variation, which is to be expected. So now I want you to think about this, and this is just going to be an experiment. We'll take a sample of size 5 rolls. We're going to take 5 of those rolls, so you could roll the die 5 times, and calculate the mean of those 5 rolls. So we get a 1, we get a 3, we get a 6, we get a 2, we get a 2. Add those up, divide by 5, you get a mean, right? If you record that down and then you repeat that 10 times, we will have 10 averages. And then we can start plotting those averages. So to just look at this distribution, look at the mean of just rolling 2 dice after 10,000 simulations, you see that we get this unimodal symmetric distribution of the sample means. Note, this was not what that that constant function that we saw with our rolls. We're looking at the averages. If instead we looked at the 3 dice average, we see that we get even more concentration around this 3, 4, and then we got some tails, which is fine. This is the mean of 3 dice after the simulation of 10,000 tosses. Well, the mean of 5 dices, you should start seeing this pattern, or the mean of 20 dices. We're getting even more concentrated around what the true average is from rolling the die. And so if you think about this, and this is the magic of statistics, what does this tell you? Well, as the sample size, the number of dice, gets larger, each sample mean is more likely to be closer to the true population mean. So we see the shape getting slowly compressed around this number 3.5. And hopefully you notice that the sampling distribution of a mean becomes normal with all possible samples of n being the number of rolls to get the average. This is the central limit theorem at work. So the sampling distribution of any mean becomes more nearly normal as the sample size grows. And this must be true that the observations are both independent and random. We have to say those. And this is true no matter what the shape of the population distribution is, as long as the sample is large enough. Think that experiment we did with the NFL salary and how skewed that data was, and yet we got from the means a unimodal symmetric distribution. This fundamental theorem of statistics. There's a fundamental theorem of calculus, there's a fundamental theorem of algebra. This is the fundamental theorem of statistics, is called the central limit theorem. This is what we've been building up to, and this is what we're going to leverage from here on out. So the central limit theorem is as follows. The mean of a random sample is a random variable whose sampling distribution can be approximated by the normal model. The larger the sample, the better the approximation will be. Bigger the n, the more closely it's going to fit to our mean. It's also intuitive, and what we just saw with the dice roll, that the standard deviation of the distribution of sample means will get smaller, aka more compressed. Everything will get more and more concentrated around the true population mean. It will get smaller than the population's standard deviation. A small collection of means should be close to the population mean and thus closer to each other. So the way we write this standard error is the standard deviation of our sample mean is our population standard deviation divided by the square root of n. So the distribution of the sample means, the sampling distribution, is a probability model that falls with the normal model, with a mean of mu, which is our population parameters mean, and a standard error. Note that I'm saying that not standard deviation, but standard error of sigma over the square root of n, our standard deviation over the square root of n. So we have introduced a new distribution that is to be differentiated from the distribution of population values. The new distribution, this sampling distribution, the distribution of sample statistic, is just that, a distribution of statistics or means. Instead of showing actual data values, we are showing the means as our points. So the new distribution has a mean equal to the population parameter, which we call mu, and a standard deviation, which we now call the standard error, that is smaller than that of the original population distribution. And it has to be. Now, caveat, there are assumptions and conditions that we, again, must check. So once again, we cannot check these directly, but we can reasonably assume, we can be reasonably confident about whether the independence assumption is appropriate. We can check some related conditions to verify that assumption. So randomization condition, the data values must be sampled randomly. I got to say that. If it don't say it, then can't assume it. The 10% condition. Again, when the sample is drawn without replacement, the sample size n should be no more than 10% of the population. This allows us to justify assuming replacement. And then large enough sample condition. The central limit theorem doesn't tell us how large a sample we need. For now, we need to think about our sample size in the context of what we know about the population. So this is a little bit different than those categorical variables. So this question goes like, which normal? The central limit theorem ensures the sampling distribution of a statistic, the mean, is approximately normal. But which normal model? Like we've learned about proportions, and the sample proportion is centered around the population proportion we call P. For means, it's centered around the population mean, which is mu. All that remains is to define the standard deviation. So the normal model for the sampling proportion has a standard deviation equal to the square root of PQ over N. We've seen that before. The normal model for the sampling distribution of means, however, of sample size N has a standard deviation of sigma over the square root of N, where sigma is the population standard deviation. Interesting. The standard deviation of the sampling distribution decreases only with the square root of the sample size. It's not a one-to-one ratio. Thus, and this is important, the variability, the spread, decreases as the sample size increases, but only by a factor of the square root of n. So if you ask 100 more people, then the sample variability will only decrease by 10. So to decrease the standard deviation significantly, we have to increase the sample size a whole bunch. But we cannot forget that we are limited in the sample size to 10% of this population. So this is this give and take that statisticians often do, is we have to wrestle with these types of concepts. So for example, and this is trying to illustrate a point, SAT math scores have mean 541 and a standard deviation of 103. What about the mean of random samples of 20 students? Note that the small sample size is okay because we believe a normal model applies to the population. They don't call them standardized tests for nothing. We are interested in the distribution of possible means from samples of SAT scores from 20 students. Like if we gave this standardized test, this SAT, on a Saturday in March, and we wanted to find the average of each classroom that is limited to only 20 students, I want to know what the distribution would look like. So SAT scores from 20 students. SAT scores have a mean of 541 and a standard deviation of 103. That's each individual student. And since the SAT is standardized, it's reasonable to assume that the model for all SAT scores is normal. What we are not discussing is a distribution of individual SAT scores. This is not like what Sally did or what Joe did. This is the entire room. What was the average? So continuing, SAT scores have a mean of 541, a standard deviation of 103. What about the mean of random samples of 20 students? So we have to check our assumptions and conditions. I need these to be met. So the 20 students were randomly sampled. It was stated there, so we meet our random sampling condition. It's reasonable to believe that the SAT scores of 20 randomly sampled students will be mutually independent as long as the students were not all from the same school. That would give us our independence assumption. Otherwise, some schools may prepare the students for the test in one way, and it's not quite independent. Our 10% condition is reasonable. 20 students represents less than 10% of all students. Under these conditions, the sampling distribution of Y has a normal model. And is our sample size large enough? 20 students provide a small sample, but we believe the distribution of individual SAT scores is unimodal and symmetric, so the sampling distribution has a normal model. We go with that? So individual SAT scores have a mean of 541 and a standard deviation of 103. What about the mean of a random sample of 20 students? Well, our mean is still 541, but our standard deviation of our sample proportion will be the population standard deviation over the square root of n. So this was sigma 103. We were given that divided by the square root of 20, and we get 23.0315. So this is our normal, what is that? This is our normal model with a mean of 541 and our sampling distribution standard deviation of 23.0315. So let's take a look at that. If we were sampling classrooms of 20 students, we would expect to get the average score of the room of 20 to be between 518 and 564, 68% of the time. Or, as I say, 68% of samples of 20 to have a mean SAT score between 517.97 and 564.03. 95% of the samples will have means between 494 and 587, and 99.7% of the samples will have means between 471 and 610. Remember, we are not comparing SAT scores of individual students. This is not Jimmy and Billy and Sammy and what they did on their test, but collectively a group of 20 students, how they did together. Now, what is the probability that a sample of 20 students would have an aggregate mean SAT score of 590 or more. So we meet the conditions for calculating the probability, which we listed before. So now we are going to write our probability statement. What is the probability that a random sample of 20 students has a score average, a mean, greater than or equal to 590? We are using a normal model, so we can go normal CDF. Our lower bound, our upper bound, our mean, lower, upper, our mean, and our standard deviation. And I'll just write this for our purposes, standard deviation over the square root of n. So we get 0.0167. Now, you could also say, what is the probability of having a z-score of 2.2361? Well, how did we get that? Remember, mean z-scores are your score minus the mean over our standard deviation, or in this case, this is our standard error. And what's the benefit of using a standard score or a z-score is that we don't have to worry about typing in the mean or standard deviation. We can use 0 and 1. We get the same thing. So the probability of a random sample of 20 students having a mean SAT score of 590 or better is approximately 1.67% of those 20 students. Now, what if I flip it? Note, this is different. If I'm looking at an individual student, SAT scores have a mean of 541 and a standard deviation of 103. What is the probability that an individual student will have a score of 590 or better? Well, we say, again, probability. Now, x, our random variable, is a student gets a score greater than or equal to 590. So we do the same thing. Normal CDF, 590 to infinity, comma 541, comma the standard deviation. This is not standard error. And we get a probability of 31.71%. Note, our distribution is different for individuals than samples. So the probability of an individual student having a mean SAT score of 550 or better is approximately 31.7%. Do you see the difference between sample distribution and individual distribution? One more example. Speeds of cars on a highway have a mean of 52 miles per hour and a standard deviation of 6 miles per hour. Mean, standard deviation, and are likely to be skewed to the right. We got a very few fast cars that drive down the highway. It's just expected. Describe what you might see in random samples, there's our word, of 50 cars. So we are investigating the distribution of sample mean speeds from many samples of 50 cars on the highway. So we need to check our conditions. Check conditions. Independent, random sampling conditions. Yep, it said we were randomly sampling. Independence assumption. It is reasonable to think that the speeds of 50 randomly sampled cars will be mutually independent. One does not affect the other. Our 10% condition, obviously 50 cars represents less than 10% of all cars on the highway. And then a large enough. 50 cars is a large enough sample to ensure the sampling distribution is unimodal and symmetric, even though the original distribution is skewed. Even if it's skewed, it's still okay. So according to the normal model, again, draw a picture and we label it the mean speed of 50 cars. We have our mean with our standard deviation, or standard error, I should say, which would be 0.8485. Remember, this is sigma over the square root of n, and this is our mu. 68% of samples of 50 cars to have mean speeds between 51.2 and 52.9, 95 between 50.3 and 53.7 miles per hour, and 99.7% of samples to have means between 49.5 and 54.6. You either give me this picture with the 68, 95, 99.7 distribution, or you write it out, but I need to see one of these two. So the question is, what is the probability the next 50 cars will have an average speed of 50 miles per hour? We have our normal model. Our conditions are met. We have our normal model with our mean, 52, and our standard error of 84.85 have been met. We go normal CDF. Our lower bound is negative infinity. Our upper bound is 50 with a mean and our standard deviation of our sampling distribution. And we get 0.0092. Again, the other option is to find a z-score. You might be thinking, why do I keep doing z-scores? You will be surprised at how simple it is to utilize z-scores when we've got so many different models to worry about. So it's useful to showcase this as well. So the probability of a random sample of 50 cars having a mean speed of 50 miles per hour or lower is approximately 9.92%. It's not a lot. So to wrap this up, to give me a complete response, once again, to ensure you completely answer a question, the following elements must be included in your response. And this is where people go, oh, do I have to do this? Yes. So 1, you need to identify the parameter of study. 2, you must determine that the sample was obtained randomly. 3, determine that the measures are independent of each other. Ensure that the sample is not too large, so that is our less than 10% of the population condition. Determine that the sample is sufficiently large that the central limit theorem ensures the sampling distribution is sufficiently unimodal and symmetric. If it's categorical, that's NP and NQ are greater than or equal to 10, or N is greater than 30, oftentimes is what we use for means, unless the distribution is known to be symmetric and unimodal. Calculate the standard error showing the appropriate values. So standard error for a mean is sigma over the square root of n. A standard deviation for our sample proportion is the square root of pq over n. Both involve square roots. We should think like that. A complete probability statement, which means the probability of who equals how equals what you did to get it. If a normal model is involved, you got to define the normal model. That means n mu sigma. Calculate any z-scores. Even if you don't use them, you got to calculate the z-scores and an appropriately labeled curve. Finally, you need a concluding sentence. After you wrap it all up, don't make the readers do the work. You have to interpret your results. So that is it in terms of this introduction to the sampling distribution and our first foray into inferential statistics. Thank you all for your attention. I will see you in the next one, Falcons.